Okay, our last presentation is by Jim Grove. Jim has been a senior project engineer for the Federal Highway Administration for the past 11 years. Previously, he was with the National Concrete Pavement Tech Center, the Ohio Department of Transportation, and Story County, Iowa. His history has focused on concrete materials, concrete paving construction, and concrete paving research. He currently coordinates and co-instructs the FHWA Quality and Concrete Paving Process Workshop.
Thank you, Pat. It's certainly a pleasure to be here today. And, I've got the enviable position of being the last speaker after four people that already talked about everything I'm supposed to talk about. But we'll try to, and I also recognize fully that I'm standing between you and your box lunch. So we'll keep this moving and see what we can do here. Before I forget it, I want to make one shameless plug for our mobile concrete trailer that's out in the parking lot out here. Once the conference is over here in a few minutes, you're welcome to come out. We'll have that open. The equipment that you saw out here at the tables, we'll have that there, plus some other goodies that you might be interested in. And I should add to that too, if you see something you like, part of our program is that we have a loaner program, and not only to agencies but also to contractors. And if you would like to borrow it, try it for a while, see if it, see what you think, and you look at whether you want to purchase it or not. Talk to us. That's certainly a part of what we're all about also. Let's see here. Here we go. What we're really all about here today is durable concrete. We've talked about that in a number of ways already. The two things, though, that I think I want to kind of just emphasize here of what we've all heard is there's two aspects that I would show. First, testing the right properties, and really that's what PEM's all about. We need to look at the properties that matter, what's going to make a pavement last, a long time and be durable. That's what we're about. The one at the bottom, though, is one we really haven't talked about too much, but it's testing real time. It doesn't do us any good to find out 28 days from now that we got low strength. We got 28 miles of pavement now that it's all bad. We don't want that. We need to. The key is doing it as we're constructing, real time, so we can monitor that variability that Gordon showed. That's inherent in what we do in our whole business here. But we need to monitor that so as those changes happen, we can adjust for them. This is a picture of the pavement in Bellefontaine, Ohio. It was built in 1891. Now, for you purists, yes, actually the 91 is the pavement I'm standing on, taking the picture. What you're looking at is 1893, but let's not quibble over 2 years. That makes it 128 years old. Now, what I'd like to challenge you today is to think about that this coming summer when you're building pavements, and think about what you're building today. Can that be still around in the year 2147? Because that's what 128 years from now will be. Now, and I think about that, when you think about that, can you, foresee that your grandchildren, one of them or something, will be standing on that pavement that you build this year in the year 2147, telling their friends that my great-grandpa or great-grandmother helped build this pavement? Now, before you think that's just totally nuts, or that I am, and there's some validity to that, but I thought about this, that my grandfather was born in Ohio, and when that pavement was built, he was 15 years old, which means that my great-grandfather could have been somebody that helped build that pavement. So that's not as nuts as it may sound. That really does work out. As we talked about a number of the speakers so far, things have changed, and we've been doing the same thing over and over for a long time for a number of reasons. But in 1922, there was a major event happened. The slump cone became an ASTM standard. So we're coming up on the 100th anniversary of the slump cone here real soon, and we're still using it. And as Gordon, or one of the speakers, pointed out, what does it really tell you about the pavement? Well, it tells you that if something's changed, and there's value in that, but it doesn't tell you whether your pavement's any good or not. And so we need to move into better things. That's what cars looked like in 1922. Luckily, we've moved beyond that. 1949, another big year, because that's when the pressure meter, the one we've been talking about that you're using every day, that's when that became an ASTM standard. And there's the 49 Chevy that a good friend of mine owns that he restored. It was his grandfather's car. That's changed a lot. And then in 1981 was another milestone when the rapid chloride permeability, or penetrability to be more exact, was invented or was worked on by FHWA and PCA. That's my first brand new inspection vehicle when I got into this whole industry. It was the biggest, that's a Ford Fairmont, the biggest piece of junk Ford ever made. Had a Pinto engine in it, leaked oil, had no power. Anyway, enough of that. You've seen us talk about the different 6 properties. The first one we'll talk about is strength, because we'll get that out of the way right off the bat. We're really not talking about anything new in terms of the PEM spec. Flexural strength, compressive strength, different states use different things, whatever works for you all. Compression seems to be what most people have gone to. Flexure, which is kind of ironic, because flexure is how we design pavement, but that's not how we test pavement. But that really won't change too much. As we talked before, acceptance and mixed design are the 2 times that we would be looking at the various tests, and the spec outlines and what tests would apply in each of those cases. The PEM came about by coming from the idea that, and this is at least the way I think about it, for too often we've been thinking of it as a one-man band. Strength was everything. That's what we measured, and if it was good, high enough strength, met the spec, is probably good concrete. Well, it may have been true back in the year, back when that slump cone came into existence. Life was pretty simple, and strength did probably relate to that, because if you screwed something up, strength is almost never going to get better. So if your strength is low, yes, it's probably telling you something's wrong. So basically, kind of a one-man band. Today, we've identified the 6 properties that I think are the key then to making sure that we're going to build durable pavements that are going to last a long time. And yes, when I made up that slide, I put the association in, and I found out there's nobody in the room old enough to know who the heck that even is. So we finally got some others, and hopefully you recognize somebody else in there that's a 6-person band. The next one was reducing cracking. And what I wanted to show here is that in the spec, if you take a look at it, in most of them, there's an item for a prescriptive spec. In other words, if we don't choose to do the testing, there's some things we can do by just a specification item, kind of similar to what we often do today. And in this case, reducing cracking would be a paste volume change. Or we can do the testing. And I was really impressed that David talked about the testing. I had some skepticism that many people would do that, but you already started, and that's really commendable. That's fantastic. There's at least a couple of versions here where we can calculate that paste content. Jogging with our trailer has developed a spreadsheet. There's some others out there too. I think CP Tech and Peter Taylor has done that, and that you can get to help calculate that. So it's, again, a very easy thing. You put in your mixed design or your proportioning, and it'll help calculate that for you. Freeze thaw, that's another one of those properties. The water cement ratio is again that prescriptive item. Those ones that are colored in that yellowy color are the prescriptive ones. The rest of them are the testing ones. I think that's important for that. Plus then the fresh properties is really what we've been talking about, the air content, the standard air pot that we use today. We're urging people to then look toward the SAM, because I think that tells us, and I'll talk about in a minute about that, but that tells us more of what we really need to know. Water cement ratio is really, in my view, just how many duckies are in your hot tub. I mean, that's really, if you want to think about it. When you've got a lot of water and not many duckies, what happens is when your cement grains start to hydrate, that whole process is a matter of they grow little fingers. As the hydration goes on, they grow more fingers, and they grab onto stuff. They grab onto each other, they grab onto sand, they grab onto rock, whatever's there. But the farther apart they are, the longer it takes for those things to get together. That's why we want to keep moisture in your concrete to keep growing more little fingers, and the longer that's happening, the more fingers you grow, the stronger the strength, the more strength you gain, the lower the permeability. We want duckies like on the right, lots of duckies, close together, not so much water. That's really what we're talking, that's what water cement ratio is all about. In order to measure that, we've often Well, with the SHARP 1 research is where the water cement ratio test came about. And that is fine, although there's some, it requires some attention. You've got to keep taking it out, putting it in, mixing it up. There's some things like that. If you lose some pieces, that can make a problem. Luckily, there's a new device that's come along, really new. As a matter of fact, you've seen it maybe out on the table, called the Phoenix. Dr. Tyler Lay from Oklahoma State has developed that. You can see there the picture. There's two of those units sitting on the tailgate of that pickup. It's really very simple. It's kind of it's the same principle. We're trying to measure the water in the mix, so you can take a sample real time right out of the back of the truck, and that way you make sure that you're accounting for how much washout water did they not get out of the barrel if it's a ready mix truck, or how much when the slump button that they're pushing that doesn't actually show up on the batch ticket. Those sort of things that we can, by measuring it, we know what we've got. The one in the center there shows there's a hot plate on the bottom. There's a pan that you put your sample in, and on the top is what Dr. Lay calls the branding iron. Picture in your oven the broiler at the bottom. When you put stuff in, and it's got the heat from the top. So basically what we're doing is putting heat in from the top and the bottom to drive out the moisture. The really nice thing about this, and I think why there's some real potential here, is you don't have to babysit it. You do all that, put it in, start it up, and when you come back and weigh it, it's up to you. If you've got to go do something, it makes it a lot quicker and easier, and I think there may be some real advantages here that you might want to take a look at, and we have one out here that you can sure look at later. We talked about air content, and others have talked about it. A standard air pot measures total air. The SAM then goes one step further to measure the property that's important, which is the air distribution. And we got enough small bubbles evenly spaced to protect it from freeze-thaw damage. Here, again, the SAM being it measures plastic air, which is the important thing, so we can do it real time, as I was talking about, and measures that air system. It really is similar to the air pot, which is really good because everybody kind of knows how that works. It's got two more clamps because we're going up to higher pressure. It's one of the differences, and it does take longer, that question that came up. I grant that. I think how you implement it is really going to be up to each state. In my view, at least at the beginning, I would certainly not see advocating throwing out the standard air pots. I think we could still use that. What we do with this is add an ability to measure something in addition to total. We're going to measure the air system, which is important. So therefore, we could continue to do what we're doing because we're really, a standard air pot is measuring consistency. And if our total air is consistent, really the chances of our air system changing are pretty small. We could do that periodically during the day. That could be the acceptance. We could end up with a standard air pot as more of a QC thing and then use that for acceptance. I certainly see that's where it's going. But every state can figure out kind of how to adapt that into their own system. What it does is something different. It does not do the same thing that the 457, your hardened air, does. It doesn't measure bubble size. It doesn't measure spacing. But what it does do, and I'll show you just in a second, is something different, and it tells us what we need to know. The reason it takes longer is you really do it 3 times at 3 different pressures, and then you repeat it. And there is an ASTM standard, so that we're ready to go. It's easy to implement in that sense. I think this explains it well as best as that I can think of. You've got you're going to the first test we do is this first one. It's at 14.5 psi pressure, which is the standard air pot. So the very first test you do should give you the exact same number that you would get if you're using the standard one. But it goes beyond that. So then you pump it up to 30 psi, and there does another reading. Now, I didn't mention, but the digital gauge on the top is recording all this, so it's not something you got to worry about. Matter of fact, it steps you through and tells you what you have to do next. So it's very simple in that sense. If you do the 30, then you go up to 45 psi. So we've got a third test at that higher pressure. Then we open the pit cocks and let all the air out and start over. Don't take the lid off. We just start with the air pressure and do it again. And so then we're back at the 14.5. We're up to the 30. We're up to the 45 psi. Why the reason that second line is higher, it takes more pressure. At least the way I think of it is it's squishy. After you've squished out so much, it takes more pressure to go up again, and therefore that next line is above it. Our goal is to figure out what's the difference between those two 45 psi pressures. That's the principle behind it. That's called the SAM number. That's the number that we're looking for. Oop, wrong one. This is kind of a visual thing. As you can see, the picture on the right is after we've got up to that 45 psi. You see there's not much left. The left one is the bubbles as they came in. The way I think is fairly valid, and to think about it is that we're doing the opposite of what happens when you open up a can of 7-Up and put it in a glass of water or in a glass. Because when you put the 7-Up in the glass, you can see now all of a sudden all kinds of little bubbles came about. Well, what the bottling company did was take and squish those bubbles into the water before you opened it. When you let the pressure off, all of a sudden the bubbles come back. Well, we're doing just the opposite. And that's what really we're measuring is how many of those little bubbles are squished out. And as you can see here, Dr. Lay did that and then did a lot of work to compare that to your hardened air samples with the spacing factor. So basically what he's saying is that what would be good concrete for either test is good concrete, and what's bad concrete is still bad concrete. And that's really all we need to know. It does it a different way, but it identifies what we need, which is this got a good air system and will protect our concrete or not? and that's what it does. Here's permeability. Water cement ratio, again, the same. We talked about that. Here's rapid chloride. We've been a lot of talk about that, so I don't need to go into it. The newer test is resistivity. And again, there's a lot of rapid chloride has been around for a long time. I think it does relatively well, although it takes a lot of work. And it's a core, and you got to prepare it, and you got all that sort of thing. The resistivity is a simple device. You've seen some pictures already. We've got them out here to look at. You put it on the specimen, hit the button, and bada bing, you got a number. And that's what we're all about. So that's why we really think we've got something that's easy to use in the field and can do that. You just saw the numbers from Pennsylvania, your own state's numbers. Here's some from Louisiana. There's some from Maine. We've got another one I didn't show of our own data from our trailer. They all look the same. It really does correlate. I think everybody's agreed it's over. Yes, we're doing some development of other tests, but boy, this one looks like it really works well with what we're already familiar with. Aggregate stability. Excuse me, that really doesn't change. And it really can't, because every state knows their own aggregates better than anyone else. And whatever you're doing to protect, if decracking is an issue, to address that, ASR, you're one of the first states that was doing that. I can remember 20 years ago or more when I was with Iowa, and we're talking about ASR. You folks were really way ahead of the curve and looked to Pennsylvania for some of the research and early work in that area. Workability, now you've seen some others talk about this. We've got the box test and the modified V-Kelly. Both of those, I think, are really the answer to that age-old question. It's sort of like the holy grail here. In my whole career, I've seen 3 or 4 people, or attempts by people, to make a test that measured workability, and it never really worked. And I think finally we've broken through that, and I think we finally got it. The box test, again, another one of Dr. Lay's tests. We look at really 2 things is what the key here is. One's consolidation, and it's a visual thing. We're not talking, decimal points and that sort of thing. Did it consolidate or didn't it? It's very simple, and that's good. That's what we need, a simple test that anybody can interpret. The other one is edge slump, which now, some people used to say that a slump cone would measure workability, which it really didn't. But back in 1922, when we didn't have vibrators and didn't have a slip-form paver, maybe it did. I mean, maybe it was good enough. It probably was. We've got a lot of pavement that's still there, so I'm sure it was. But anyway, today we do use a slip-form paver. We do need to know those things. I see this as a real tool for the mixed design phase. I don't know that there's a lot that we gain by running this in the field during production, because as I've heard many people say many times over the years, the best measure of workability is a slip form paver, because that's really where it counts, and we're already doing it out there. But when we do need to know that is when you're doing the mix design in the middle of the winter in some lab, you need to know, is this going to go through my paver next summer when I'm out in the field? You don't want to wait till you got 100,000 ton of rock sitting there and realize, oh darn, this doesn't work. You want to know early, and I think that's what the real value of this. It's simple. There is it's in the PEM spec, and there is a AASHTO is considering this for a standard. So I think hopefully in the near future we will have that. That'll make it a lot easier for everybody to specify too. This is really what it looks like. There's different ways. Dr. Lay's worked on some different, this is kind of the early approach, but I think it's simple and I think it's good. Number 1 is a really great mix that consolidates well. Number 4 is one that doesn't work hardly at all. And then 2 and 3 are somewhere in between, so you can just visually look at it and see, okay, is this what we need or not? Do we need to make some changes? The other thing is the edge slump, and we've seen both of those there on the right. Either the bottom slumps out or top down, or even the top will come over. We've seen all that. So and it really does a good job of identifying that. A couple of examples. Here's a project we were on just a few years ago. We didn't do it before because that's not how it worked with our lab, but once we got out on the project, saw what was going on, we were able to, if you can see up there in the top, look at it was really a tough mix to close. They were really fighting it. Well, when we did the box test, we found out why. It didn't work. And, you know, had we had that and been able to use it ahead of time, the contractor may have been able to make some, and in fact they did. This is the one direction. They did the next year, they did the next one, and they did find a way to make that a much better mix. The next project we went to after the first one was project, I'll call it B, and here you can see that the test, you can see, look at the edge. It was showing that, yes, we're probably going to have some edge slump issues. Well, you can see what we found out in the project. Now, that isn't how it looked the whole project, but there were times that it did. So when your water got a little high, sure enough, it started to act that way. So it really convinced us that, yes, I think this is telling us the useful information that we need, and we're really onto something here. The VCALA, this one was developed by Dr. Peter Taylor at the CP Tech Center. It basically took a Kelly ball. California is the one that really started this and has used it for many years. I'm not sure that many other people have, but you can see there in that top photo, you drop it down and see how far it penetrates. What Dr. Taylor did was add a vibrator to that. So the way that the test works is that you start out and let the Kelly ball drop like it usually does, turn on the vibrator, measure how fast then it goes into the concrete, and that can give you some numbers. The bigger the number, the more responsive it is. And one of the things I think this offers is that a way to look at optimizing your mix, because you actually have some numbers to work with. This is an example. This is kind of one of his early charts, but I think it illustrates it well, where the bottom line is the green one. All 3 of these are the same mix except different gradations. The first one is no optimization, just a mix you threw together, and you can see it never actually got up to the line. That 0.7 is not really a magic number. It's more of a band, but I'm using that just to illustrate. That's kind of the center of it, but it was never going to be a workable mix. The next one was a better gradation, and finally the one at the top, the darker blue or black, whatever color that is the optimized mix. And what I'm pointing out here is that if this is the line, which this 0.7 is the line that tells you that it's going to be a good workable mix, with a better gradation, you could drop 25 pounds of cement out of that mix and still get the mix that works just as well as the other one. And a way so therefore is a tool to be able to optimize, reduce cement content, save some money, and still have a really good mix. So that's really what I see some of the value there. Just to kind of to wrap up and to kind of repeat what I'd said, but the test properties again come from the PEM. The strength is unchanged. The cracking tendency is at pace volume is really one of the keys to that. for freeze thaw, not only water cement ratio, but our testing, and Sam being the one that, in fact, this now will be able to measure the property that really counts, which is what we really need to do that the air pressure meter never did. And the other one then is the aggregate, or the permeability, again, water cement ratio, and either the rapid chloride or now the surface resistivity. That's the one that I think we'll see more, and as we get more familiar with it, there's some little things to tweak and kind of define with that, but I think we're getting close. Aggregate stability is as always, and finally workability with these new tests with that. And with that, I think I made it in my time anyway, and hopefully lunch is still there for us.